Mic check. Mic check sounds good. Mic check 01. You know, I couldn't get to the end without one last rap. So we're coming back into you. Mic check 01. I hope you had fun learning about programming in COMP1511. We're now here at the end of our time. There's no more lectures and there's no more rhymes. But whether we've finished, we will never diminish. So remember what you've learned and let yourself shine. That's my final rap for COMP1511 in 2020. Good morning, everyone. I hope everyone is reaching a point now at the end of the term where at least some of the things that you have done have finished. You're able. Oh, Giro-chan, I will miss all of you as well. It's been a fun one this time because I never expected I would just be freestyle rapping in my lectures. Yeah, but I hope everyone's getting to the point where a lot of your second assignment is finished. And hopefully as I go through this recap of the course and things, stuff starts to stick in your memory. So stuff starts to feel like, yes, I've seen that before, you know? And when we get to that, yes, I've seen that before feeling, it doesn't have to necessarily be a, yes, I know exactly how that thing works. So long as it's a, yes, I've seen that before, that's enough, you know, you will, that means that you'll get it eventually, you know? So, I mean, I'm not giving up the opportunity. I've thrown into the lectures today a tiny bit of continuing about pointers and reminding about some of the issues that come up with pointers. I'm not sure if anyone can see in the background. I brought a little wisdom with me just for fun. My little life-size Yoda plushie. I've got it sitting behind me, so it's offering wisdom. Probably in the recursion bit, I will start speaking in reverse in Yoda speak. Okay, so where are we right now? What did we cover on Tuesday? Tuesday we were looking at the exam format. We looked at the rough difficulty of the different questions in the exam and some advice on how to approach the exam and how it's going to get started. Tom put together a little thing for everyone in the revision section that is now open on the course website. So if you look up WebCMS, you'll see there's a revision heading in the left sidebar now. There's also in the first thing, I think in the revision section, there's a list of questions that we have that are either past exam questions or questions that we think are very similar to exam questions, and we've got that there in a way that's that shows what which ones are close in difficulty to the levels that we're pitching the exam questions at. So if you want to, you can go back and look through. I think those things also say which lab they're from as well. It's like this question from this lab or weekly test, and it says which questions it kind of matches up with, so you can go back and do some of those questions again, or even just look at them and say, okay, this is the level of difficulty. And if you want to, given that list of questions, you can put together for yourself a set of 8 questions, and you go, okay, this is roughly what I might see in the exam. So you can actually build your own practice exams out of those example questions. And if you have a look at them and where they're kind of pitched and what's in them, you could even put together other ones out of other examples. The other thing that we were doing last week is we looked at the first part of COMP1511. So we went through our kind of initial learnings on technical C programming, so lots of little things like variables, if statements, looping and things. But you'll notice that this time around, when I go through it, I'm assuming the knowledge that you have now. So it's a little bit more than a little bit more than what I taught you originally. So when I taught you originally, we were building stuff up piece by piece. But now that we have the whole thing built, we can say, okay, this thing actually relates to all these other things as well. So when I looked at looping when I initially looked at looping, it was just like, okay, we're going to go through things multiple times and then stop. Nowadays, we know we've got one kind of loop that goes through an array, another kind of loop that goes through a linked list. There are other loops as well. I didn't show you all possible loops, but sorry, bit of background noise there. Might shut the window. Yeah, but once we know the structure, we will be able to use it for many different uses or use cases, I guess we could call them. So today we are going to continue the speed run of COMP1511. Juno's asking about when the final exam is. It is from 12 to 6 p.m. on the 4th of December. So, if I am correct in my thinking, it is exactly 2 weeks from today. So, because I think it's on Friday, yeah. Yeah, Friday the 4th. So, it is, oh, Girichan. Way to bring on the heart attack. That would be pretty funny. No, so you've got 2 weeks to study. There are some sort of help resources for study. There is a study session happening this afternoon, although I assume that in the study session this afternoon, people might be asking a little bit about the assignment as well, which is fine. CSC Soc is running that, so there's a link that's gone out in, I think, multiple weekly notices. A link has gone out about that, so check your email if you want to join in. I'll be around for a little bit this afternoon for that one. Next Friday, I'm planning on doing another live stream, so I haven't decided when during the day it'll be, but I'll hop on for 2 hours. No plans. I'll just hop on, and if people want to, they can hop on and say, I've been studying this, but I don't quite get it. Can you explain it again or something? And I'll go back through the slides and go, okay, so this is what we mean when we say this or that. Or just a little demo of how I would program something, that kind of thing. Miguel, you'd be very sorry for being late. I rapped at the start today. It was the last rap as well. Having said that, you can always go back and watch it again. Of course, I rap at the very beginning so that, like, anyone who watches the video can see the rap. Obviously, the most important part of the lecture. Okay, so today, what we're going to do, speedrun the rest of the course. So there's a lot of things that I talked about that are not C related, but very, very related to programming. So these aren't just the non-technical. Well, actually, like, there's a lot of stuff we talked about that we're doing in C that is very useful programming skills. But there's a lot of programming skills that are not related to the creation of, like, just the raw creation of code. Miguel, go back and watch it now. It's alright. I'm still introing, although I'm about to get into it, so up to you. It's only, like, it's pretty short. It only took me like 10-15 seconds to get through all of it. So yeah, we're going to look at the non-technical things, some of which are very, very important, because when I talk about stuff like problem solving and debugging, that's really, when it comes down to it, nearly more important than being able to know the language itself, because if you don't know what you're going to write, then there's no point knowing the syntax of the language. And then we're also going to go through the second half of the course, so all the technical bits of the course. So let's roll straight into it. Let's first look at all the little bits and pieces that we talked about. These are all of the topics, so I didn't put these topics in the list on Tuesday, but here are all the topics I've taught you that are different things that are going to come in very handy. So we looked at stuff like the history of computing. I didn't actually put a slide in for the history of computing because I think when I covered the history of computing, it was basically 1 or 2 slides as it was, and it was very very anecdotal rather than like a comprehensive history of how computing got to where it is today. So I'm not really pushing that idea that much. I think if you wanted to study the history of computing, there's probably things in an actual history course that might be more interesting than what I know. because historians are going to look at how computing has affected humanity and culture, and the way that we've moved forward because of the different things that computing has changed. So I think that would be probably more than I could teach. But things that I do know very well are the engineering side of things, like problem solving, making your code reusable, working with other people, fixing errors, and things like that. So let's have a look at some of these slides. Again, the continuation of what I was saying on Tuesday. All of the memes in these are memes that were provided to me by students. So this is a classic one. I mean, like, I would be happy to put this kind of image up as well myself, because I think this happens a lot. It is. And I think we looked at this like when we were doing debugging and stuff. It was like you could fix it, but you don't really know why it's fixed or what's going on. But it is working, and you're like, I fixed something, but what I fixed is not what I thought the problem was. I thought it was something else entirely. Yeah. So a couple of people in chat are already saying, yeah, this is exactly me. Okay, so when we are looking at problems in code, if you get to a point where you really need to think about something, generally that means that the problem's bigger than you can handle at that point in time. Or you don't understand what's going on, but maybe if you break it down into small parts, you'll be able to understand a part of the problem that you're trying to solve. So I'm always looking at any kind of problem and trying to break it down into parts, so that I can say, if I build this thing to do this part of the problem, I build another thing to do another part of the problem, I piece those things together, then chances are I'll solve some or all of the problem. So this is a skill in terms of looking at something and it looks insurmountable when you first see it, or it looks massive. Like I say to you, I want an application that does full management of song playlists and libraries, with a whole bunch of different methods for searching through them and stuff like that, and bang, just make it happen. What we want to do is get ourselves away from the idea of bang, make it happen, and go towards, okay, in order to do that, I'm going to need these tools. These tools are going to be made up of these parts, and these small little things are easily kind of digestible, understandable problems to solve. So what I'm going to do is I'm going to focus on one at a time, get them done, and then build them together into larger things. Very, very much a sort of a modern engineering way of looking at problems is that if you look at the giant problem, it can reach a point where you're like, oh, I don't even get what's going on with that. But if I start breaking it down to small bits, I will be able to complete those small bits. And so that's an easy way for us to think about problems. When we're functionally going ahead and doing things, it also makes it easy for us to test individual parts. We haven't had a huge amount of time in 1511 to talk about testing, because we're just kind of pushing a whole lot of new techniques and ideas and trying to get you creating stuff as much as we can. But I hope we've at least shown you a little bit of the idea that if we test individual components as we're going along, then we know that those components work, so that when we attach them to other components, we know we can kind of decide between which ones we think are most reliable at that point in time to see which one, where we need to do our debugging, that's where we can split things apart like that. So pretty handy skill, being able to separate things and test them. We looked at code style as well, and so this was a line I think I gave at the very, very beginning. Actually, it wasn't the very beginning. It was pretty close to the beginning, where I said, like, when we write code, it's half for the machine and half for humans. When you first think about what programming is, when we think about it as a concept, as an idea, we very much think about it as talking to the machine, and so we think about writing code, and we think the entirety of the code we write is for the computer. But then the more you do it and the more you think about it, the more you realize that a lot of what we write in code is for humans. So it's either for ourselves, so that we can understand what we're doing better, we can actually fix our mistakes better if it's written in a way we understand, or it's for working with other people. So as I say here, just tapped my touchpad by accident. I'll use my mouse over here. How readable your code is directly related to how efficient it's going to be working on it in the future whenever you need to go back over things. And this obviously makes a big difference in efficiency once we're working with other people. So we try to maintain a particular kind of standard with a group of people when we're working together. And if we can do that, we can find our problems more easily and fix them more quickly. We can also get help from other people more easily if they can read our code without as many problems as we could cause. And I remember the demo of really bad code, and it was kind of funny because we were all laughing at it because I just compiled all of the coding the sort of code style errors that I'd seen in a couple of decades of programming and put them all into one tiny program. So it's funny to watch, but then also when you think about it, you can see by that extreme example the difference between if you can read code well versus code that's nearly been made specifically to make it harder for you to understand. We also looked at code reviews. So I know this is a weird thing to say because we're here in university and I'm saying to you, don't show your code to other people, like your assignment code. No one else should look at that except for subject staff. Don't even talk about your specifics of your assignments with each other because that could end up with you and someone else having code that's really similar. And that rings a whole lot of alarm bells in the back end, and we say, well, these people didn't work individually on this, we can't assess them. So you're in a weird situation at the moment in university where we're trying to make sure that you, as an individual, get all these particular skills. So we need you to work alone so that you go through this journey of learning and understanding on your own. But once you get out there and you start really making code, so you're in a research group or you're in a company making apps or anything like that, you're going to be pretty regularly looking at each other's code, because when it comes down to it, putting multiple programmers working on things, there's a bit of an overhead because you've always got to communicate back and forth between you who's working on what and things like that. But when we work together, we get bogged down in problems a lot less because you've got times and ways you can bounce ideas off each other. So we looked at the idea of code reviews, and we've been doing a few of those in the tutorials whenever there's time. It's a smattering of it. We've probably done 3 or 4 of them in the tutorials over the term, but at least you've seen the idea that you can look at other people's code and be able to give feedback to each other without tearing into each other over how well or how badly things work. But getting a chance to see how other people code, as well as show other people how you code, gives you this kind of nice balance of sort of give and take of ideas, and even simple things like structural layout of code. If you never coded with anyone else, you won't even know if your layout is something that's working for everyone around you. So there's this nice combo like that where if we regularly look at other people's code, we're both going to teach and learn more about what we're doing. Debugging. I can't remember. I heard this quote a very long time ago, and I think it's hilarious, but I can't remember where I first heard it from. But yes. Debugging is being a detective in a situation where you're the criminal. So we've built all this stuff and we've built problems into it by accident, and this always comes from us slipping up somewhere, us making an assumption about something, us not knowing entirely what we're doing with our programming, and then we need to find out later after the fact. We need to go back and find out what went wrong. Always really funny because I could say something like it's us not fully understanding what we're doing, and that's the reason why we need debugging. But I don't think there is anyone in the world who is programming. I'm going that far to say this is like a blanket statement of everyone that's programming has to debug. There's nearly no one who is programming at a level where they don't have to debug anything. And if they are, they might be it might be a sad situation of them always programming things that they already know the answers to. But generally, when we're going to be programming, we're going to be making stuff we don't know the answers to. In which case, we're going to make mistakes, and then we need to learn how to debug. So we need to learn how to go back and remove the errors that we put in the code. So, a lot of the details about programming, we looked at two particular kinds of errors, and so we could separate all of the errors that we had in 1511 into these two in a sense. So the syntax errors are logical errors. The syntax errors are the code language errors where we may have a perfect idea of what we're supposed to do, we may have a perfect plan for what we're doing, but we have just made a small mistake in how we translate that into C. May not be a small mistake, might be a gigantic mistake. Oftentimes, mistakes that don't take many letters to type in can be gargantuan mistakes when it comes down to the effect they have on the code itself. We also have logical errors, so it's quite possible to create code that compiles perfectly, code that even runs, but it doesn't do what we intended. Or it does exactly what we intended, and then we look back and we say, oh, that doesn't... what we intended is not actually solving the problem that we had. So we get these two different errors. One's like a nuts and bolts error, which is the syntax errors, and then the logical errors are more what we'd think of as planning and design errors, nearly. So we looked at specific techniques for how we might do testing and get information about our bugs, but the first thing I always say is get more information. So if all you know is that your program is not working correctly, then the first thing you're going to want to do is say, okay, exactly under what conditions is it not working correctly? Can we isolate which part of code is not working correctly? So if we want to, we can look and say, okay, which function were we in when it stopped working? And then we go, okay, that's where we start our search. Let's look at that one particular function and say, why is that particular thing working or not working? And then if you have to, you go back in time and say, that function I think is working correctly because I have this test case, this series of test cases that test this function. And they seem to be checking all of the things that I think are the issues with this one particular function. So this is why in assignment 2 we have a section where you write tests for specific functions. I always kind of laugh about this, right? Because I think a lot of people are potentially going to write a lot of code, and then they go over to their test file and they try to finish stuff in their test file and then they submit. Whereas the way that we would actually want to do this often when we're working in a commercial context and stuff like that is sometimes we will write the entire suite of tests first. So we'll say, this is exactly how things should work. This is how we're going to test whether they work. And then we will write our code that does the functional bit after our tests are finished. This is very, very much simulated in the idea that we give you auto tests. So if I was to give you auto tests, it's like having a requirements and testing engineer kind of person set up this test suite for us and say, okay, all we need to do is fill out the tests that happened. And then we can work in these small chunks, knowing that each of these small chunks is going to be tested very, very accurately, and then we know which things are working before we move on to other things. So if you've got those tests, it'll always be easier to get more information about what's working, because you can say that these particular parts of the program are thoroughly tested. So we can narrow down which parts of the program we want to look at. What are we saying here? Yeah, Miguel's saying it's always really bad when your errors don't come up until a few functions later. Yeah. And you noticed that you had a pointer that you made null and you hadn't realized, and then only 300 lines later in your code did that pointer actually get accessed or something, and then it looks weird, right? Because you just go, why is this breaking now? And then this backwards trail through your code to find out where these variables all came from. So this is the art of debugging, right? It's about narrowing down what might or might not be the problem, and then winding back through that. Oh, Miguel, I remember that one. I think I saw that email chain. It was a question about whether DCC was acting differently from GCC and things. I didn't really know the answer, but Andrew Taylor, who has lectured this course in the past, answered that question in via email. So there was like interesting stuff. I think it's most likely that it was broken in either compiler, but DCC is polite enough to actually tell you when things are an issue. Okay, so the trick with debugging is always more information. Do we know where the error is exactly, and do we know which parts of our program are interacting with the error and how? And do we know which parts of our program are feeding information towards the point at which the error happens? So, as I was saying before, separating things into parts helps you isolate which parts you know are working, and you don't have to test those. And also, when we think about logical errors, we want to always bounce back to what our initial intentions were, and then is our code actually reflecting those intentions? So this is why I talk about drawing pictures of what you want your code to do. Like those little diagrams, all that MS Paint stuff that I've been doing is I'm not just doing that because I'm in a lecture and it's a partially visual presentation medium that I'm doing. I'm drawing those diagrams because I literally will draw those diagrams when I'm writing code. I think one of the funny things that we get down to once we start working a lot with programming is that we consider the computer to be the primary tool of a programmer, but if there's a second tool for a programmer, it's a whiteboard. It's like bouncing all these ideas up on the whiteboard. Yeah. Miguel, yeah, so you'd been using GCC, but it was a broken way that you didn't notice. So it didn't crash, and it still produced the right output, but it was leaving a time bomb for later. Those kinds of logical errors actually may not always be logical. Sometimes those are even syntax errors that your compiler's not picking up. Those are the most devious ones. So something like a memory leak is a syntax error, but it's a syntax error that your compiler won't tell you about. And those kinds of things sometimes don't cause any problems until your program is scaled up to a certain point, or your program is used as part of another program that, like, say you build something into a library and it's used as another program, and you don't realize that you've then inserted a memory leak into someone else's code. So you won't even know about it until like 2 years later when you're not even looking at it anymore, and someone says, hey, after we added your code to our server, the server started falling over once a week. And it's like, oh, all right. So it's funny how bugs have a way of lying dormant for years and then coming back to bite you. Right. Sorry, I'm just reading Miguel's things. There's a particular situation that he got into with assignment 2, I assume. Okay. We also talked about professionalism. And I really wanted to kind of, if you didn't see this, it's because it was in week 6. So it was one of the bonus lectures in week 6, but we were talking about how there's a lot more to computing than just writing code. And there's a lot more about being a professional who works with software. And I think if I was going to boil this down, I had 4 points. I was talking about communication, teamwork, resilience, and actual programming itself. And not just programming, technical skills. And the first 3 very, very much come down to the idea of caring about what's going on. So if you're caring about what the work is that you're doing, and you're caring about the people around you who may be interacting with your work, that leads into learning about communicating with other people, working in a team. I actually think that there's a lot of really specific skills you can learn for working in a team. There's a lot of technical tools and other things like that. But when it comes down to it, if you care about the other people in your team and you care about what happens to them, everything else sort of flows on from that. So I was like, if I wanted to, I could just remove all of these points, and just say, please give a shit. If you do, it makes a difference, right? So if you care about the stuff that you're working on, it makes a difference because it sort of makes you want to do a good job. And if you like, because if you hit a point when you're working on something and you really you don't want to do it well anymore, you're just like, I just want to get this done. I don't really care about how well this works. That means you may have hit a point where you need a break, you know. And again, this also goes back to care. This goes back to the idea that maybe you should care about yourself more than your work. And that's a balance that I think a lot of us have a lot of trouble with. So, you know, I had years working as an engineer. I've had years working as a teacher as well. And in all of those situations, I've had to balance, you know, how much work I'm putting into my job, and if I want my job to always be producing the best possible work, am I burning myself out then to the point where I can't get any work done at all? Am I potentially sacrificing my future work on behalf of my current work? So that's a decision that one must make, and I think that comes from deciding how much you care about different things. And so I think this is something that's always going to be important. And when we look at teamwork, we also want to kind of bounce back to a lot of the research that people have done in what is effective teamwork, and generally the more effective teams are the ones that support each other rather than the teams that are purely made up of highly competent individuals. I mean, the best, if you can get it, is highly competent individuals who all support each other, because generally no one is a highly competent individual without having had some support from other people along the way. And the more we do that in a team, the more we can grow the team we have into amazing workers. And hopefully everyone will get to that point sometime during their careers in whatever you're doing, because I know that there are people who are in COMP1511 who aren't necessarily looking at a programming career in the future, and that doesn't matter because this professionalism stuff is not limited to programming. But the idea that if you do end up in a team where you're supported and you support other people, you'll notice, because those are the ones that we stick around in for a long time, and we say, okay, this is something I really want to be a part of, and I really want to, you know, contribute to the success of this group and stuff. So it's a lot of fun like that. Yeah. Okay, so I've got a break here. It's a little bit early for the break, but it sort of sits in between the technical stuff and the non-technical stuff. So, Kira-chan, if you care about your paycheck. Yeah. So, what I might do, I'll do this slide, and then I'll go back to talk about the break, and we'll take an early break, and then we'll go through all the technical stuff afterwards. So I wanted to talk about my experience. So the My Experience survey is the UNSW's system for tracking your feedback about courses. So I just want to point out that I read every single response in the My Experience surveys. So I'm going to read everything that everyone says in this course about it. I'm going to put all that together, and every term that goes into my little bank of these are the things we need to change for next term or next year and things. Some things are huge, and I say I can't change that until the end of the year when I've got a couple of months to work on things, but some things are during the term we're going to make some changes as things go. So things that are happening in course structure, you may even notice some of the experiments I'm doing midway as they're happening. So if anyone noticed, I think it was week 8 or week 9 tutorial which had the subject headings in it. So all the tutorial questions were separated into this subject, these questions, this subject, these questions, that kind of thing. That's something that I'm looking into for structuring tutorials so that they're easier to use. That feedback is something that came from last term and is slowly working its way in. So if you have any feedback from the course, anything that you think we could do differently, we can improve. Anything in the course that stood out to you as being really useful to you, things that made certain topics click better than other things. Throw that stuff into the feedback, because the course is, I mean, I don't know, up to you, not me, but I think the course is in a reasonably healthy place at the moment, but the only reason it's like this is because of the feedback we've received, and because we've worked with the feedback we've gotten from students to just sort of incrementally improve the course. So you're getting the course at the moment. For me personally, this is my 6th iteration of teaching COMP1511, and you've seen little things like recursion came back into the course when I realized that we had space for it, and we had some feedback about different topics and ideas and stuff. So little things like that add up, and it's best if the changes I make are based on your feedback. You know, if I'm not doing this for you, for the students, then why am I doing it at all, frankly, you know? So getting your feedback is really important. So if you haven't already, please go to myexperience.unsw.edu.au and give us feedback about the course. It's entirely anonymous as well. When I say I read everything, it gets collated together, and I read them, and I don't get to know who's saying what. So if there's things you need to say about things that didn't work, feel free, because I think that when stuff is or isn't working, when there are issues, sometimes I won't know about all of them, so it's good for me to know. Alright, so let's go on break in a moment, but on the way to break, I wanted to offer you a thought exercise, in a sense. So this is a question for everyone, is why are you doing what you're doing? I love it. If I just leave it there, it's really funny. Why are you doing what you're doing? It sounds like I'm an angry mother or something like this. But some of you are doing computer science. Some of you are doing a related field that happens to have COMP1511 involved, or a gen ed because you wanted to know something about computer programming or working with computers. And hopefully you've learned something from that. But the question is, why are you doing what you're doing? Because when it comes down to it, it's easier for us to do things if we know why we want to use them. This is a classic thing. I don't know how many people are straight out of high school here, so they're in their first year of university. There's so much stuff that we look at, and I remember saying this when I was in high school, where you look at something and you go, I'm never going to use that again. I don't know why we're learning this, because I don't know where this goes. And I think that's because when you're in high school, the world is trying to prepare people for all the possible things they might do. So it's really funny when someone says, I'm never going to use this. And then I've had this situation, it's really funny, where I was teaching people how to make computer games. And I was like, so you learned trigonometry and linear algebra, right? And so then now we're going to use it. And they're like, oh, I didn't pay attention. I would have paid attention if I knew this was how you make computer games. And I was like, yeah, well, that's the way it goes. Not everything can be put into context, because only you, out of your entire high school, ended up here needing this information about computer games. But now that we're in university, now that we're at a later point, we're much closer to seeing exactly how we're going to use these things that we're learning. So if you have a goal, you have something that you want to do with your degree, it's good to think about what that is. So you could actually, it could be simple. It's like, I just want to work in the computing field. I heard it's a good industry. I think that computing is the industry at the moment that is shaping the future of humanity more than any of the others. I'm just sneaking in what I think about it. But maybe that's what I want to do, right? So I want to get into these kinds of things, and so that's why I'm learning what I'm learning. That allows you to focus on what you're learning, because you know you've got an end goal. And then if you know where you're going, you can say, okay, I'm going to use the time I have to push myself. I'm going to push myself towards those particular things. Kira-chan, I'm doing this course because it's a prereq for 2521. That actually is a thing that happens for a lot of people. They say, this is my goal within the university. what does a university think I need to know to reach that goal? So it's like, I want to do data science or something like that. I know there's some data science students here. In which case I want to learn how to build deep learning, artificial intelligence algorithms. So what are the courses I need to do to get to the proficiency necessary to start building those things? And so this would nearly definitely be one of them, because COMP1511 is kind of the prerequisite to all other computing courses. It's very hard to do any computing courses without having done 1511. The caveat I put on this about thinking about your goals and your future and all this kind of stuff is you don't need an answer yet. You don't have to say, I know exactly where I want to be. You know, like I don't know if people have done job interviews, and they ask you, where do you want to be in 5 years' time? You don't have to have that answer. And I know in the job interview, people are really going to want you to have that answer, but I'm talking about what's actually valuable for you as a human being. It's not necessary that you have to have that answer yet, but it's good to at least ask the question. Because sometimes you can say, what do I want to do in the future? Where do I want to be? What do I want to like? What effect do I want to have on the world, or something like that? And the answer to the question might lead you to not needing to be where you are right now, or looking for an alternative to what you're doing, and that's not necessarily a bad thing. You know, a lot of people think that, like, if you don't finish the degree you're in right now, that you're some kind of failure. But when we think about the statistics of what degree students initially enroll in and what degree they leave a university with, there's a significant amount of drift happening between different possible programs. And that's not a failure, that's people learning about their direction and choosing a direction as they learn more about what they're studying. And Miguel's saying, literally changed the degree from mechatronics to comp sci plus mechatronics because programming's great and it's the only course I've been good at. Yeah, it's easy sometimes when you look at something and go, wow, I don't know why, but I'm better at this than I am at other things. And when that clicks, you're like, oh, okay, maybe I found something that works with my brain better than other things. Let's go deeper and see where we go. Okay, so we're going to go on break now. It is 11:44, so we'll take exactly 5 minutes break. Come back 11:49, and then I'm going to launch into the second half of the course from a technical perspective. And we're going to go through all of the topics that we covered and at least say a few words about each one. And I have a section where I digress later into detail about pointers and structs and things like that again, because that's something that I still want to teach again, because I know that it's the kind of thing that helps a lot for understanding those difficult things. All right, be right back. Very interesting conversation going on in chat at the moment about marks. And the difference between what is and isn't important with marks. Very good point what Rosie makes at the end there is that the difficulty is that marks are important to students because people will judge you based on your marks. So, yeah. And I think as Gira-chan's saying there, if you were chasing high ATAR, it doesn't matter as much now that you're at uni. You need to chase uni marks, not high ATAR marks. However, getting into uni at all required high ATAR marks. And then when you start working, it's about learning about how to work within the company you're working in, rather than how your marks were at university, because you'll have shifted into a different context. And then when you move from one job to another, there's only a certain amount of that experience that can actually be carried between the jobs. So it's a difficult world. I mean, like, especially for me, when I went from being an engineer to being an educator, I had to throw a whole lot of stuff away, you know. But then there was other stuff that I'd learnt earlier on in my degree that came back when I started teaching. So there's a lot of, weird and difficult things. And I think it's like, the question we're asking is, how do you navigate life? And it's like, well, that's hard, isn't it? Like, there's no easy way around that. So as Eric's saying, where might be able to help you get into an interview or something like that. It might change if you're doing engineering. It might change what level of honors you receive when you finish at UNSW, that kind of thing. I mean, for some people, WHAM is like, this is the thing I need to get to stay in university as well. So like, we have to think about that difficulty also. So there's a lot of things where, the university kind of lives and dies by these marks. But they're a distillation of what you've learnt, in a sense. Like, if we wanted to really measure people, we'd have to measure how much they learnt, how much they understand, and what they're doing. What we're hoping is that marks reflect that. But marks aren't just used as an assessment tool. They're not just used to say, this is exactly how much you know. They're also used as an incentive tool. So they're used for us to say, do this because it's going to be important for your learning, and we'll give you marks nearly for free for that. I'm looking at labs and weekly tests here. Significant number of students are capable of getting 100% in labs and weekly tests because we give you plenty of time to work on each of those. If you get it wrong, you can just go back and do it again if you want to. As opposed to the exam, the exam's going to be real raw. It's going to be whatever you know and can deliver in a limited time. Yeah, so you get this kind of different thing happening there. Anyway, interesting discussion, but it's a discussion for a later time. Miguel says, people shouldn't be based on their marks. They should be judged based on their marks with a C, which is why we should all be trying to do the final exam using only recursion. I want to see if that happens. I don't suggest it. Please don't take that as a suggestion in any way. I think you should, regardless, you know how I'm saying all this stuff about, like, they're not super important and stuff like that. I still am going to give you advice, all the advice I can give you to maximize your marks, because the marks don't come from me. I have to measure them, but I'm measuring them on these objective rubrics and stuff like that. So I'm happy to say to people, this is how you maximize the marks, because I don't scale them. So if people take up the tactics that I've given that maximize their marks and the average for the subject goes up, that's a good thing. It means people are understanding what's going on. So when I say do the entire exam with recursion, I am not saying that is a good tactic for the course. You might learn a lot about recursion though, but recursion is only one technique. And if you throw the other techniques that we've learnt in 1511 and you give up your opportunity to show how well you know them, might not have been such a good idea. You may find that at some points, though, once you've got a little bit of experience with stuff with the recursion, you'll notice the times at which recursion is better than just straight out line by... What would I call it? Declarative? I don't know if I'm getting my terms right. Declarative or procedural programming. is not as effective as recursion in certain circumstances. And we showed one really, really particular example of that in the lectures, but understand that that was a very, very contrived example. I went out of my way to find something that was hard to code in one way but easier to code in another. Detecting those examples in reality is much harder than it was in the lecture. Mega Grog is saying printing stuff backwards. Yeah, and printing using a standard library, as Gira-chan says, maybe is a better way to go about things. Okay, let's get back into the slides. I've talked about my experience already. So, technical things. We're going to go back into these technical things, continuing the list that we're looking at previously. So, one of the topics that we learnt next, I think this was still in the first half of the year, term. I keep thinking that every term of COMP1511 that I teach is an entire year, and I would probably be forgiven for thinking that 2020 has been going for 3 years now. So, we introduced a new variable type called char, which was an 8-bit integer, and I want to call this an integer because it's funny, because nearly everything that we've been storing in memory for C could be considered an integer. So structs are just one really, really big integer, because we can think of an integer as a series of bits, you know. We can likewise think of all of our data structures as just a series of bits. Just ones and zeros that we're using. So the character is something that stores a number in the same way that a pointer stores a number, or an int or a double stores a number. This is specifically, though, an integer that uses ASCII encoding to represent a character. When we chain these together into strings, so words, sentences, things like that, they're arrays of characters. Because the length doesn't really stick to one specific length, when we're looking at words and things like that, we're usually going to have an array that's bigger than we need to be. So we need to have something in the array to say, this is where the letters that we care about end, and everything after this in the array is just sort of empty space. So it can have any kind of gibberish in it, because we're not going to read it unless we need to, expand the string longer later or something like that. So we use the null terminator to be the marker point inside the array to say everything after this is not important, but everything before it were the actual letters in the word. And good point here, as Gira-chan was talking about using standard library stuff, there's a lot of standard library stuff that makes common operations for words easier. So the string library, but also it's good to check out the C-type library as well. That's a library dedicated to individual characters. Because every now and then you want to loop through a whole string of characters and say, I want to look at each letter one at a time, and I want to test whether they are one thing or another. Rosie's asking, is it possible to declare a string without size? If so, how will we know how big it is? Do I have code for strings? This is code for using strings, not for declaring them. Yeah. If you look up some of the early code I showed for making strings, if you declare a string and you initialize it while you declare it, so you initialize it with the double quotes, the way that gedit will do this is it will show you the difference between a variable and a value that can be put in a variable. So a value that can be put in a variable will always be that pink, the fluoro pink text. So that is actually a value that can be put inside a string if you use the double quotes. String's the only array that you can initialize like that. And so what it will actually do is it will look at the number of characters in the double quotes string, and it will make the array exactly the size of that number of characters plus 1 for the null terminator. So it'll be that number of characters plus the 1 for the null terminator, and that's how big your array will be. So if you declare a string without any specific size, but then you say this is the thing it's initialized at, it will use exactly enough memory to initialize that string. So you can do them that way. It's mildly dangerous because if you ever change it, you don't know how big the maximum size is for that array. so you won't know how many letters you can fit in there. But if you're making a string for a one-off usage or something like that, then it works pretty well. Miguel saying, if you wanted to, you could malloc the size of a string, and anytime it got bigger than the size of the string that it needed, you could allocate new memory for it for a new size. So you could have a string that could grow as the program runs. Yes, and you might actually be stumbling upon a variable, well, not variable, but a collection type called a vector. I don't think a vector is a C thing. I think I'm in C++ land again here. But there are things like arrays that change size as the program works. But they're literally doing what Miguel's saying there. They actually reallocate memory when they change size. So halfway through your program running, when you go off the end of your array, you have something else to say, okay, instead of that being an array out of bounds error, we're going to create a new array that is bigger than the previous one and allow you to move into that space. So what it does is it allocates new memory for the new array. It then goes through, I'm going to lean back so I can wave my hands around more. It goes through and copies everything from the previous array into the new array, and then it deletes the previous array. So it frees the previous array and gives it all back. So the new array then has longer capacity. I'm going off my screen anyway. Has a longer capacity, but has all the stuff in it that the previous one had. So it looks to you like it hasn't changed, but it's actually moved into another part of memory, which is okay until you have pointers to the previous one, and then you've got all these kind of issues. So lots of fiddly things, but yes. Kira-chan saying, a vector is math, not computer science. Yeah, there's one of the downsides, I think, of computer science being a very late field of science, and some could say, and I would agree, that computer science is just applied mathematics. So we borrow a lot of names for things, and then sometimes the names that we borrow for things don't end up being exactly the same as they were. So the vector is a data structure, but when we consider a vector in maths is a series of numbers. The vector data structure could be a series of numbers also, so it sort of works, but it's become something different. Yeah. And Raymond's saying C++ has a string data type, so you can actually just work with strings as well. Yeah. Okay, let's not go too deep into all that stuff. So we've got some code for strings here. Hopefully people are reasonably understanding some strings. So if I make a string of a particular length, we're going to assume there's a hash define here somewhere else. We can fgets into that string, so we can take stuff from our standard input and we can print it back out. If we want to, we can also loop through strings, and the key element of looping through strings is stopping on the null terminator. So we will loop until we hit the null terminator, and if we hit the null terminator, then we will stop. Usually we will not consider the null terminator to be part of the string. It's the marker point that ends the string. We also looked at structures. So structs are our first custom variable type. So this was the first time we were creating a variable type that didn't necessarily exist before. And we were building these up out of bits and pieces of other variables. So each struct was potentially going to contain multiple other variables. Structs can't contain themselves. They can contain pointers to other versions of themselves. Actually, I never really said that structs couldn't contain themselves, but if you think about it logically, if something contains itself, then the one inside it also contains itself, and the one inside that contains itself, and that contains itself, and so we have an infinitely growing data structure. The first time you declare it, it will then declare itself, and then itself, and then itself, and it'll take up so much memory that your process will probably be killed. I can't remember whether that will trigger a compiler error or not if a struct tries to contain itself, but it definitely won't be able to run. Anyway, when we have a struct, it's all in one piece of memory, but it's got lots of different types of variables inside it. And we use particular operators to access the fields, which are the variables that are inside the struct. So a dot operator, if we have a struct itself, the dot operator allows us to access something inside it. If we don't have the struct itself, but we have a pointer to the struct, we use the arrow or the stab, as some people have been calling it, to access the fields inside. So if we have a pointer to something, we use the pointy operator. If we have something, we just use the dot. That's the way I try to remember the two of those. What are people saying? Yeah, Miguel thinks that a struct containing itself would cause a compiler error. I have actually written code like that before, but it wasn't exactly the same. It was the idea of a linked list, but instead of having a pointer to the next node, it actually contained the next node, because things got really complicated and I forgot what I was doing. And so instead of, I had an array of pointers to other nodes, and I accidentally had an array of nodes. So when I was initializing my program, I created one node, and then it created an array of other nodes. They all created arrays of other nodes, and I hit like 4 gig of memory usage on initialization within a second or something like that. And then my program just died, and I was like, oh, okay then. That's an issue. I think that wasn't even nodes of themselves. That was structs containing other structs, but then those things were cascading. So you can definitely cause problems like that. People are talking about converting things to other things. Oh, the difference between using fputs and printf %string, Raymond's asking. There's actually functionally very little difference between those two. They're going to look nearly identical when you run them. I think the difference is when you do fgets. So if you do scanf %s, a whole lot of things break really easily. That's why we haven't taught it, and we don't even suggest you do that at all. But if you do fgets, you can grab a line of text and then do stuff with it. If you do scanf %s, there's no guarantee it actually fits into the string that you're writing into, so you can get array out of bounds errors and all this kind of stuff happening there. I think there's a lot of text chat there, but I'll leave that for the moment because I've got to get back into talking about what we're talking about here. Okay, so structures, and we've got some code here. I actually got some fresh code that I wrote for this, so there's a little theme going through today's lecture. So let's say I'm making a spaceship, and it has a name, and it has a number of engines and the number of wings, because we obviously know that in space, where you don't need wings at all, that measuring spaceships based on the number of wings is very important. So we've got this spaceship that I'm creating. It's a struct. So after I have declared the struct, it becomes a variable type that I can use again. So struct spaceship is now a variable type, and I'm calling this particular one X-Wing, and I'm saying its name is Red 5, and it has 4 engines and 4 wings. If anyone doesn't know what I'm quoting here, this is one of the famous ships in Star Wars. So today's going to have a little bit of a spaceships in Star Wars theme to it, because I was just having fun with that. So if I then want to make a pointer to that, I can use what I know about making pointers to say a pointer is the address of something. So this is the address of that variable X-Wing, and I've made a struct spaceship pointer. So this was the point in the course. I always laugh when I accidentally make those puns. The point in the course where our variable types got really long, but that doesn't mean they're not variable types. It just means there's more information in the variable type about telling us what it is. So struct spaceship means it's one of these. The star here means it's a pointer. So the type of my ship, the variable my ship, is a pointer to a spaceship structure. So if I was to follow this pointer, I would get to one of these if it's been assigned to one of those. If it's null, I obviously don't get to one of those. But this one it's pointing at this particular variable, which is one of these, so it's all correct. And then if I want to access the fields inside by the pointer, then I use the arrow. So this engines is the same as this engines, but we're acting on the idea that sometimes we have a pointer, but we don't have the variable itself. So if we don't have a named variable itself for something, chances are we have a pointer to it instead. And that's going to happen a lot of the time when we memory allocate something. When we memory allocate something, we don't actually have a variable. We just have a piece of memory. And the only way we can access it is via a pointer. So the only way we can get into the fields is by using the stab like that. And it's much easier than the alternative, which is to use the star to dereference the pointer and then the dot to access the field, which gets messy. because they're particular in their order of operations about which one goes first, and so you've got to put brackets around the star and then a dot afterwards. So too fiddly. It's much easier if we use the stab, and it does it for us. Okay. Some random guy's asking, is anyone able to explain what a global buffer overflow error is? I forget which one the global buffer is. I know there's several buffers that are in use, but in general, a buffer overflow is if we have a particular piece of memory that we're allowed to use and we go outside of it. So there's the stack memory, and then we've heard about Stack Overflow stuff mainly because that's the famous website, which is like, here are our coding problems and how do we want to fix them. And one of the biggest coding problems you can get in C is the Stack Overflow, where we've gone outside of our instruction set by accident. Girachan said struct formatting is definitely a question on the exam. So, I mean, it's highly unlikely that anything that I have said in the previous lecture and this lecture isn't in the exam. It's highly likely that all this stuff is in the exam somewhere. Except for the non-technical things. I'm not going to ask you how much you care about what you're doing in the exam. I think that's something that's really for you to work on. And that's one of those things that has no marks attached to it, but is potentially more important than everything that does have marks attached to it. But, you know, it's the way it goes. Onto memory, because memory and structs are closely linked, because most of the time when we're using structs, we're going to be putting these in memory. So at this point in the course, we started thinking about what it means for stuff to be in memory. So all of our code is in memory, and all of our variables are in memory. So for anything to work on our computer, the information about it is stored somewhere in memory on our computer. So when we edit our code files, they're on our hard drive. When we run our code files, they get copied into the RAM, which is the faster memory on the computer. Individual parts of that code, as it's running, get copied into the even faster memory on the processor. So everything's faster and smaller. Remember that diagram of like faster, smaller, more volatile, larger, more stable. If you want to go to even larger, more stable, you can look at like offline backups of data. So everything in CSE is backed up somewhere else. I don't know if they're still using it, but I remember back in the day, UNSW used to have these massive tape drives. So like there were these reels of magnetic tape where you could copy everything that's happening in UNSW onto this magnetic tape and then put it in a cupboard and say, we're pretty sure that this tape will keep its data secure for the next sort of 5 to 10 years before the magnetism in it finally degrades. So those backups will last that long, and we can go back and get them later if we want to. So we can think about the bigger the storage is, usually the harder it is to get stuff back off it. Within our computer ourselves, we don't think about more than the hard disk. Hard disk is the biggest, slowest one. And then the actual, what they're called registers that are on the CPU itself, they store very, very small amounts of memory, but they store exactly the stuff that the CPU is working on right then and there. So all of our stuff is in memory. Oh, we had some questions there. Alfred's asking about... Let's go back here. About the difference between my ship and X-Wing. So X-Wing is a variable that exists in memory. My ship is the address of X-Wing, which means if we're using the address of something, we can access the things inside it because we know where it is. So it's kind of like my ship being the pointer to the X-Wing means it gives us access to it. They're not exactly the same thing, but, you know, they give us access. Mechagrog, create a recursive function which finds and prints all the possible meanings of life. That's a bit awkward. I think it's well, okay. It has to be a really, really good function that can work differently for everyone, because everyone's meaning of life is different from other people's. Which is why, as Will says, it repeats 42 on loop. That's a little Hitchhiker's Guide to the Galaxy quote. If you're ever looking for an interesting book to read and you're a bit bored, I highly recommend. It's a lot of fun. Anyway, let's go on. Okay. So we have different portions of memory that exist for different things in our code. So every time we open curly brackets, it's nearly like we have a stack of memory, and every time we open curly brackets, we add another thing to our stack. And that thing has its own instructions and its own variables. Every time we add a function that adds something to the stack, it has its own instructions and its own variables. Whenever those curly braces finish, that thing falls off the stack. So it gets pushed off the stack, and everything that was in it will disappear. So the thing that we can remember, this is the easy way to remember it, what goes on inside the curly braces stays inside the curly braces. So when we are finished with these variables and the curly braces close, the variables will disappear and their memory will disappear as well. The only thing that will last longer than the function or the curly brackets that it's created in is explicit allocation of memory, and we've learnt about using memory allocation and free to make that happen. So I can have a function that says create a linked list node, and I know I want this linked list node to connect up to other things, so I want it to last longer than the function that makes it. So in that case, I'm going to use memory allocation to say this piece of memory, never clean it up. So I don't care how many closing curly brackets you see, never clean up this piece of memory, it's mine, I want to use it. So that way I can have, so for example, assignment 2, I can have a bunch of playlists, and I can keep going into functions, out of functions, and other places, but those playlists are going to remain there because I explicitly put them together. If I do want to say, yes, okay, now I'm finished, now I don't need that memory anymore, I will tell you when. I will free it when I'm done. So that's the balance between memory allocation and freeing memory that we will be doing ourselves. When we are doing memory allocation, we use the macro size of, which tells us exactly how big a data structure is. I suggest, it's not a hard and fast rule, there might be other ways that you might do it, but the majority of the time when we use memory allocation, we use size of as well. Like we very rarely find a situation where we wouldn't use size of with malloc. So we can get into this instinct of always using this. I have a pointer to a particular thing, a spaceship, and I malloc the size of that thing. So this one line here is nearly always going to be the same in everything that we do with pointers. With memory allocation and pointers here. So I've got some other code here to make another spaceship, so we're assuming we have the same struct that we've declared, and now this time we're memory allocating the spaceship instead. So there is there's no variable inside this curly brackets for the spaceship. The variable is made outside of the curly brackets in a sense, somewhere else in memory, and so the only access we have to it is this pointer here. So I can set up this other spaceship here. This one is called the Millennium Falcon. It has one engine and no wings. So I don't know why it's such a popular spaceship. It should probably have lots of wings if it wants to be more popular. Anyway. So people are asking some questions about modifying the X-Wing and stuff. So the My Ship was a pointer to that X-Wing, or in this case, the My Ship is a pointer to this piece of memory. And this piece of memory doesn't have anything in it to begin with. But once we have that pointer, we know that at the other end of that pointer is a piece of memory which is exactly able to store a name of a particular length and 2 integers. And so we can go in using the stab and we say, okay, go in here, copy this into this, and set this to this and set this to this. So in that case, what we can do is we can say, okay, we can set this up exactly. And then I can say, oh, I lost my ship in a game of Sabak. I don't know if anyone is any full-on Star Wars nerds here, because then you know how this happened. So I lost my ship, so I'm going to free it, and I'm going to give this memory back, this memory that I'd allocated previously. I don't know why. I don't know why YouTube tried to hold that message for review. Sabak is for losers, hollow chess gang. So there's an old fight that goes back and forth between people who like spaceships, between those of Star Wars and those of Star Trek. And they're all pretty awesome spaceships, and that's what Mega Grog is alluding to. Wait, Holochess isn't... No, sorry. Holochess is actually the game on the Millennium Falcon, isn't it? So I guess you're just staying within Star Wars. No, is it 3D chess or Holochess that is the Star Trek one? I don't know. I digress. We're not going to go any further into that. But anyway, the style question was: do we write size of space struct spaceship, or do we put size of and no space here between the brackets? I would suggest put the space, because this is a macro, not a function. When you're calling a function, you don't put a space because the brackets are kind of attached to the function call itself. So these are the inputs that are going into the function. Whereas the space here is like the space on an if statement or a while loop to say we've got a keyword and then afterwards we've got some other stuff that's happening. So it's not directly, it is kind of directly related, but it's like one thing and then another thing. Whereas the string copy here is all one thing together. In fact, this main, sorry, let me say that this as a function is usually not done with a space, whereas this as a keyword that has something afterwards is usually done with a space. So your ifs and whiles are going to have a space, but your functions are not going to. That's usually the way that we do it, because things are more closely attached to functions, whereas I guess this struct spaceship can appear elsewhere, like it does here. Will's asking, if we free a struct with another struct inside it, does that struct get freed too? That depends on how you have done the other struct inside. So, if we have an example of a struct that contains a pointer to another struct, then the other struct is not inside it. And so if the other struct is not inside it because it's a pointer to another struct, you've got to follow that pointer through and free the other thing first. But if the struct is just inside the other struct, so if I have a struct spaceship inside something else, but it's not a pointer to a struct spaceship, it's actually in there, its memory will be contained inside the other struct's memory in exactly the same way that every variable inside struct spaceship is inside struct spaceship's memory space. So if we free it, everything inside goes with it. So the difference is the other thing actually inside it, or is the thing that's inside this struct only the address of the other object? If it's only the address of the other object, you still need to go to that other space in memory, that other address, and clean that up first. So you get different things. Your second assignment has a lot of structures that are pointers to other structures because it's linked lists, as opposed to if you're using the track time struct. I think a lot of the time when we use the track time struct, it's just put in there. It's like another variable that's just put inside the struct. And so you don't need to explicitly free that because you don't have a pointer to it. So there's no memory location for it. You just do that. So yes, Girochan, I'm probably giving away. I mean, not necessarily. I'm talking about the theory of removing memory for structures, not necessarily how you do it for the specifics of the assignment. But, you know, there's some useful stuff here that you may want to use. Cool. Okay, so as we got to this point, we are able to create structs. We're able to memory allocate structs. We then extended this one level further, and we created linked lists. So structs that contain pointers to the same type of struct. And that allowed us to chain together these nodes, that we call them, into lists. And Zol Kierkegaard is asking, if I free a pointer, the struct it's pointed to is freed. Yes, that's exactly how free works. Free can only work on pointers. So free is something that is very much about memory, not about variables that exist in the normal flow of our program. So you can't call free on a normal variable. You can only call free on a memory location. So you're saying that's why stage 3 isn't working. Well, I'm glad that even though we're doing a recap here, people are still learning things. That's really cool. Okay, so let's look at linked lists. Linked lists are how we extend what we were learning before about pointers, structs, and memory allocations. There's a lot of stuff that goes into this. Linked lists are pieces of information that store some kind of data, and the data could be huge. Like those of you who are putting together playlists and tracks and stuff know that this data might not be, this memory is not to scale, obviously, so this data might not be the same size as the pointer to the next node. It can be huge. But the trick is that these things all connect to each other, and the convenience that we get from linked lists is once we've figured out how to use them. I mean, obviously everything in programming is like, it's complicated if you don't know how to use it. It gets easier once you understand how to use it, and then you understand the convenience of why we have something like a linked list. They're not a fixed size like arrays, so they can shrink and grow, and they'll use exactly as much memory as they need at any particular time. The other thing is you can insert and remove individual elements from the list, so you can insert at any point in the list, or you can remove any element of the list, and you don't have to do any shuffling or anything like that afterwards. You just move some pointers around and it's fine. With an array, if I was to remove an element and say I want everything in this nice order with that one element gone, I have to go through and grab all the other elements and shift them up one, so it's a bit of a cumbersome process. Linked lists reduce the need for that. They have a different overhead in that every element is in a different place in memory, and every element requires this extra sort of overhead of having a pointer to connect to the next one. So there's pros and cons of each, which is why we learnt them both instead of just saying there's only one way to store a lot of information. Because it's really, really useful to be able to use both of these, because they're going to be used differently in different situations. That's, as you go further into programming, you'll see these kinds of things. Back to the memes. So if a function removes an item from the linked list, the second item says, "I'm the head." I love that all of these memes that I was given have just got this like really, really excessively edited format just to make sure that they work with programming. It's like, how much did they have to black out to get this one to say, "Alright, I'm the head"? Yeah. Anyway. Will, you want to talk about night moves? We're definitely not going to talk about that now in this lecture, but I can show you ideas about that. Maybe we'll see if later on today in the study session, if there isn't much else happening. But I have a feeling in the study session there's going to be a lot of much more pertinent things being learnt about. So it is interesting that something like night moves has a really easy technical solution if you have learnt about that particular kind of structure and way of traversing a structure that you will see in the future. That's a reason why it's that question in the tutorials and it's not in the exam anymore, because if you know the other technique, it's easy. And if you don't know the other technique, it's hard, and you need to piece together 1511 stuff. So the intention for the question was you got to piece together some difficulties in working in COMP1511 to put it together. But the downside is if someone else has already learnt about I'm gonna give you the keywords like game trees and backtracking and stuff like that, then it becomes really easy. That's why it's not a valid exam question anymore. Because I don't want an exam question to be something that someone with prior knowledge can get really high marks in and someone without prior knowledge can't. It has to be from the course. You have to be using what you've learned in the course, or else it's not proper assessment. Which is why it's only an example question now instead of one of the core questions is actually in the exam rotation. Miguel said, "I just brute forced it by simulating literally every move." Yeah. And Megagrog said breadth first search, which is very similar as well. So both of those things are going to brute force every possibility for every possible move that the knight can do, and then put them in the right order so that you only select the ones that are in the alphabetical order of the ones that actually met the goal. You're not far off, both of you. Yeah. So some random guy says night moves was easy, so maybe you'd seen the kind of techniques before that lead you to that. Anyway, let's go back to the lecture. Oh, easy to fail. Right. Okay. So, linked lists in code. The code's getting more complicated now. So, let's say we've got locations. And we have locations that are in a linked list. So, each location has a name and there's a next. And so, we've got this simple function that adds nodes. And what it will do is when you add a node, you tell it what its next pointer should point at and what its name should be. And we've got a couple of these are planets here, so I'm continuing on this spaceships and planets thing. So we have Tatooine and Yavin 4 as these two particular planets. These are both from Star Wars, by the way, that are being added to a linked list. And so I think we've seen code like this a fair bit now. The really common pointer to the same kind of struct, so pointed to another version of the same struct, and then some information. So we've seen this kind of thing before, and we're talking about how we put it together using another function. Let me just... I have nowhere to put my face. Okay, so I'm just going to move myself out of the way for a moment so you see complications in pointer structs and memory. So I want to do a little bit of a little session on this. So this isn't purely revision. Oh, I guess it is. This is me going over the details of this again. Let's think about carefully what a pointer is. A pointer is a variable that stores a memory address, right? So I think I've said this many times, but I think it's important to think about this. It's still a variable. So it actually exists in memory somewhere, but the trick is the number it stores gives us access to something else. So think about the word address. The word address is key to what a pointer is. A pointer is storing the location of something else. So if we change a pointer, if we change the pointer itself and not use a star or a stab on the pointer, so we change the actual number that the pointer stores, what we're doing is we're changing where the pointer is aiming. That doesn't change any of the variables that are at the other end of the pointer. It just changes which variable the pointer is aiming at. So we need to know the difference between changing a pointer versus changing the thing that's at the end of the pointer. So if I give you a piece of paper that has UNSW, Kensington, I forget, 2021? I can't remember the postcode, something like that. And then I say, you can follow this to UNSW. But I'm saying, don't follow this to UNSW. Change what's written on that piece of paper to, I don't know, time for Thai, somewhere on Anzac Parade, further down Kingsford. Time for Thai is a restaurant that a lot of students go to. I think it's just this cheap Thai food. So what I'm saying is, rub out the address that was there before and write a new address. Note that me doing that does not change anything about UNSW, right? So I can change a pointer without changing the variable that's the other end of the pointer. So remember that you can change the address that's on the bit of paper without changing the thing that's at the other end of the address. That's something that's important. Then we think about the star. The star says I can access the memory location. So it's nearly like me saying, if I've given you an address on a piece of paper and then I say the star, what I'm saying is follow that address to where it is and now do something with what is at the other end. So I'm saying the memory address that I had in my pointer, I will now go to that memory address, and now I will be able to change things at that memory address because I've made it there to that location. The star takes us there, and it's called dereferencing because the pointer is a reference to something, and the dereferencing is saying, okay, no longer a reference, I want to physically be at that position. So we actually go there. So we need to sort of see the difference between what happens when we change a pointer versus what happens when we change a pointer and we put the star on it. So the star says go to that location, then change the stuff that's at that location. We also have the stab, and the stab is even more specific than the star. It is a dereference, so it's still going to that location, but it's saying go to whatever's at the end of that pointer. I expect that pointer to be aimed at a struct, and the arrow says I am now going to go to one of the fields inside that struct, and then I'm going to say read that field inside that struct and do something with it. Kira-chan saying UNSW equals null. I mean, it's not as null as it used to be. There was a period this year that UNSW was completely shut down, but now we can actually go back there. And Miguel's saying, so using the star is effectively like driving up to UNSW in a bulldozer. Kind of. Because if whatever address we use with the star gives us access to it, so we can change it, we can put new values in there, we can make any changes we want to if we use the star on something. So yeah, it is like going up to UNSW, and the bulldozer allows you to knock down buildings and put up others. Well, hopefully you're going to put up other buildings. Yeah. So we can get a situation where structs contain pointers to other objects. So we can have chains of pointers where I can go, these aren't probably not the actual variable names of what these are going to be in your assignment, but I could say I can go to a library, and inside that library I can go to a playlist, and inside that playlist I can go to a track. So each one of these is saying go to the struct at the other end of this pointer and then get more information inside. This is more abstract than your actual variables are going to be, but you get what I mean, right? Because I wonder if that's right. I've got diagrams for the assignment, but I think just want to kind of talk about it rather than going too deep into it. Make a UNSW buildings equal to null. Yeah, we could level all the buildings at UNSW. I wonder about a future where UNSW is a concept and not a physical space, where there is some kind of stuff in the physical space, but a lot of our classrooms and things like that are going to be entirely virtual. And so you could say all the buildings at UNSW become null, and it would actually do something because the buildings are actually made out of software. Trent saying, please no, I live in a building at UNSW. Yeah. So, yeah, we're talking about UNSW going into the astral plane. I think about like this cyber astral plane as being something. I mean, like we're here right now, right? We're here in a virtual classroom, and I'm talking to you in a virtual classroom. People are talking back to me via the live chat as well. We're not that far away from all of us being in something like a VR headset or something and actually just being in a classroom together and getting to, at least in a certain way, react physically to things, which might be nice. Megagrog is asking if I'm even real. I mean, I'm obviously an AI construct based on a complicated personality simulation. That's why I'm asking everyone to put stuff into my experience, because the modification of the personality construct is based entirely off your my experience feedback. Thank you very much, Megagrog. That's very nice of you. Okay, so complicated pointer code. Let's look at some complicated pointer code and see how this works. So we create a linked list with two locations. So the first location was Dantooine, and then Alderaan replaces Dantooine as the head of the list. So there's a list with Alderaan as the head, and then Dantooine as the second element. If anyone's a Star Wars fan, I'm very, very strongly referencing the original Star Wars here, Episode 4. And then we can create another pointer that's pointing at Alderaan. That's named Alderaan, and it's pointing at the head. So it happens to be pointing at Alderaan because Alderaan is currently the head of the list. And then I do something. I say, okay, that pointer that's aimed at Alderaan, I malloc a new location struct there. So the question is, what has happened to the pointer Alderaan that was pointed at the head of the list? And what has happened to the head, which also was pointed at the head of the list when I do this malloc? And we need to think about what is actually happening here. So I have a pointer pointed at the head of the list, and then I have the memory allocation here that I use a pointer that was pointed at the head of the list. So, anyone who may have seen Star Wars, it kind of looks like what I'm doing here is I'm taking the pointer to Alderaan and I'm allocating new memory over it. i.e. I'm destroying Alderaan by mallocing new memory over it. But let's have a look at what's actually happening. Okay, so we've created this thing. We've created a linked list of two locations, Dantooine and Alderaan. Dantooine we're not really going to use in this. Dantooine's too remote to make an effective demonstration. I just wanted to say that. I just wanted to say that's a direct quote from the film. So, Alderon here has the head pointer pointing at it. Its next pointer points at the Dantooine node in the linked list, Dantooine's nexus null. Basic linked list, right? We haven't done anything weird yet. But the weird stuff comes in when we say, okay, this line of code, a new pointer called Alderon points at a copy. It copies itself from head, because it says, I'm going to copy head, which means whatever address was stored in head will now be stored in Alderon. So both of these pointers are now pointed at Alderon. Then we get to this weird line here, where I've said, sorry, I just tried to select that, but it's a slide. So the head is now equal to a memory allocation of something else. So am I allocating memory on top of the memory that was there? But now we need to think about, how does basic C work, right? This is a funny thing, because this is going down to like really, really basic C. So it might look like what I'm doing is destroying the memory for that head node, because I'm allocating new memory over the top of it. But what malloc does is it says to the operating system, I'm going to give you something. I'm going to ask for a certain amount of memory, and the operating system says, yeah, sure, I'll give you that memory somewhere that's free, and I will tell you where it is. And head equals something replaces the value in head with a new value. So if I'm going to replace the value in head with a new value, what I'm doing is I'm moving where the head aims at. So we're at this point, and then we do this line, head equals memory allocation of a new piece of memory. This new piece of memory gets created somewhere else. It's not part of the linked list. It doesn't go over any of these nodes, because when I memory allocate, I use a free piece of memory that wasn't used before. And that's what this does. Malloc will create this new piece of memory. It doesn't have any information in it yet, because we haven't actually set up the information. It's alright, it's not part of what we're thinking about here. But then we set head to that new location. So we change where head is aiming by saying, okay, this pointer now has a different address than it had previously. It now has the address of this here. So what we get is this pointer is still pointing where it was before, because we didn't make any changes to it. This pointer has not made any changes to this node, because we didn't use a star or a stab or anything on this pointer. We're changing the pointer itself. If we change the pointer itself, the only thing that changes is where it is aiming. So the head had been aimed at the first element of the list, Alderon here. The head is now aimed at this new thing that has just been created. But it didn't make any changes to the data that was there previously, because the only thing that was edited was the pointer itself. If I wanted to change something inside one of these, instead of this line, I would have said head, arrow, something, and then I could have changed one of these. But since I didn't use anything else on the pointer, if I'm changing the pointer itself, that's moving where it's aiming. So I just wanted to show these little things, because I know that we could all use a refresher on this. So as I'm going through, and as I was going through and doing the revision, I was like, I want to show this again, because I think that if we want to look at what I would consider to be the hardest thing that we've learnt in 1511, it's fiddling around with pointers, because they're fiddly little things, and they're a variable, but then the value that they contain is another variable in a sense, so it's a bit weird. Megaro was asking, what would free null do? I don't know if free null will accept what you're asking, or it will say that you can't do that. So I don't know whether, because I know that free null is definitely wrong, and that free can't perform its function on null, because free says, give me some memory that has been allocated and I will give it back. So I don't know what kind of complaint you'll get if you try to free null. It might say you're trying to access a null pointer. It might also just silently not do anything. So it might say, I don't have to do anything because you're trying to free something that is not a memory location, so it'll be fine. But I have a feeling that if you run free null in a program... Ooh, hi Tom! I didn't know you were there. Tom said it's actually defined to do nothing. So if you do free null, it won't actually do anything. I mean, a better answer I should have said to that is fire it up and run it now. Because this is it, right? I have 16 minutes left to continue teaching you for COMP1511. I mean, I'm probably going to do a live stream during StewVac, so that I'll keep teaching you a little bit more. But I've only got 16 minutes left. So what I should be teaching you now is not the answers to these questions, but the way in which you can find the answers to these questions yourself. So the answer in your head, when you have the little mark in your head, I will sit on your shoulder during the exam and you can go, hey Mark, imaginary Mark, what do I do here? And imaginary Mark is going to say to you, you got this, you can figure this out. Fire up gedit DCC, compile it and run it, see what it does. You know, if we can get to that point, and then you can be like, thank you imaginary Mark, I don't need real Mark anymore. Real Mark gave me enough, so now I've got imaginary Mark forever, and imaginary Mark is going to say, I know you can work this out. There are enough techniques that you can use to work this out. So I think that maybe the answer I should have said was, it's not relevant whether I know this or not. This is something that you will figure out. Because you could say, what would this code do? And you say, well, let's run it, and now I know what this code will do. Except if it's like delete all files from your hard drive or something like that. Raymond was asking when the live stream will be. It's definitely going to be on Friday next week, because I'm actually going on leave for a little bit. I need to take a little bit of a break, but I'm back on Friday, so I think what I will try to do is do it in this same time slot, because it's a time slot you're used to, or maybe later in the afternoon if I feel like, you know, more people are awake in the afternoon than in the morning, but most likely it'll be in the same time slot. Cat, I'm like Nanny McPhee. When you want me but no longer need me, then I have to go. That's a very like kind of Mary Poppins thing as well. It's like, if you learn enough from me, you will never need to talk to me again. And that's in a little bit sad, but also in a little bit like that is the empowerment of you learning enough that you don't need teachers anymore. And everyone's going to reach that point where if you need teachers from that point, it'll be an optional thing. You'll go and say, okay, I would like to learn this thing. I can learn it myself, but it'd be quicker if I get someone else to teach me. But for all this basic coding stuff, I've now got enough momentum of my own that I will not really need a teacher anymore. And that's where I want to leave this if I can. Okay, so keeping track of pointers can get really fiddly. So I could have something called library, and the head of the library, the head inside the library is a playlist. And then I can go to the next, so that's the second playlist, and I can go to the tracks inside the second playlist, and the next of that, and that should be the second track inside the second playlist in the library. And I had to think about that. And this code might work in a whole bunch of Spotify implementations that people are working on. But whether I want to see this code in something I'm trying to debug is a very, very different question. So, yes, pointers can do this. If you've got pointers within pointers and linked lists within pointers, there's a whole bunch of stuff you can do. It's just super dangerous, right? Because, again, it's like massively indenting things. If we put too much indentation on stuff, we get to a point where we don't remember where we are. It's like if I say to you, turn left, then turn right, then turn left twice, then take 2 steps forward, then turn right, then turn left twice, and then take 2 steps forward. Now where are you? Right? It's actually pretty simple where you are. I don't even know. I got confused as I was saying it. But that's the point. It's confusing. So the more we ask a human to try to remember, at one point, Girichan thinks we're back at the start. I mean, we might be. I don't actually know. Or maybe you didn't follow any of my instructions, so you're still sitting in front of your computer. But anyway, that's the thing we need to be careful of with programming in general, is how confusing can we make it for humans. There's a threshold for confusingness for humans that we make, and if we can get to that threshold, then it becomes very, very difficult to use our code in the future. So always think about that. So completing what we're talking about here. Changing a pointer changes its value, which is a memory address. So if we change a pointer, that will change where it's aiming. It won't change any of the things that it was aiming at. However, once we use the stab, and this works with the star as well on the pointer, we're now looking at the thing that is at that location. So if I use a stab, I'm now looking at a field inside a struct, which means I'm not changing the pointer anymore once I've used the stab. I have dereferenced it, which means I've followed it to the memory location, and then I've said, now access a field that is inside the struct that's at that memory location. Rosie says, will other comp courses examine style? Yes. They may not all teach you as much about the nitty-gritty and basics of style as we've done here, but some will to a certain extent. But I think a lot of the computing courses that follow from this one will definitely give style marks for a lot of the stuff you're doing. So I don't think that you hit a point where you don't get style marks anymore until very, very late in computer science. And at that point, you will get marks on whether you were able to complete something or not. And once we get to like 3rd and 4th year courses, you simply won't be able to complete them if your style isn't at a certain level that you can understand what you're doing. Because the harder it gets to debug things. So this is kind of like setting you up in the future. Yeah. So as Tom says, yeah. Some will assess you directly on style, and some will just give you complex enough problems that if your style isn't good, you won't solve them. Unless you miraculously get lucky and get it right the first time and don't do any debugging, which is so super unlikely. Okay, next thing we did was we started using things like arrays and linked lists and stuff to build abstract data structures. So, this is the more correct version of this meme where you don't need to black any of the bits out of it. So if we pop the item at the top of the stack, that item says, I'm a head out, and SpongeBob goes off on his way. So we looked at stacks, but more importantly than just stacks themselves, we looked at the idea of what an abstract data type is. And so I rolled this in, so I could have talked about multi-file projects earlier, but I didn't. So I was just going to roll this all together into abstract data types. So when we create an abstract data type, we will have the functionality that the data type provides in a header file. We'll also have the type def, which is saying, okay, this is a type of an idea of a variable that doesn't have any underlying capability that you can see when you're using it. And so we hide all the underlying capability and the underlying data structure. But when you're using it, you look in the header file and you go, okay, I have this concept and these functions that will run on it. And the functions will say, okay, this is what it can do. And the implementation is hidden in a C file. And this means that if the only way you can access this data is through those functions, then each of those functions can check that the request you're making is valid before it changes the data. So if we don't give someone access to the actual piece of memory that we're using to store something, and we only say you have to use these functions to get there, then what we're saying is you can't access this incorrectly. Because the only way in, it's like gatekeeping, the only way in is you have to answer these 3 riddles. And if you answer them incorrectly, you're not allowed to change the data, right? And so that works really well, because it means that if someone else is working on accessing the data type, I don't have to explain to them all the nitty-gritty details. I say, these are the functions and this is what they'll do. If you call the function incorrectly, you're still not going to break anything. Oh, well, hopefully. And that way, someone doesn't need to understand any more than what's in the H file to use it. We've got a really good example of this now in the second assignment. We're going to get something like 500 submissions of the second assignment, which is going to have all these different ways of solving the same problems. But when we run our testing on things, we'll be able to run our testing. It's going to work. And we're going to see that many different people with different solutions are all going to give us the behavior that we expect to see from the abstract data type. Will's asking, don't you compile the main function with the C file though? Yes, we do. we are going to compile the main function of the C file, but we're talking about the functions that use the abstracted data type itself. They're kind of a barrier between what the main function can do and what the what you can get access to in the ADT itself. So I think what you're asking there, Will, is like, since we compile them all together, the abstract data type C file as well as the main, isn't that going to mean the main has access to those things? The main sort of, but doesn't have access to those things. It's all compiled together into one program. But if you don't know the right names, the hooks to get into things, C won't allow you to access that other code, even though you've compiled it all together. So in the header gives you the hooks into particular points in the other code, but it doesn't give you the hooks into the struct itself or into like the helper functions or anything like that that's going on underneath. Yes, I think we're talking about the same thing now. You're saying the person with the files, so the main function is kind of the person with the files. Oh, right. So the person who has the files could edit the C files. Yes, you could. So if you're working in a group together, and all of you can see all the files, and one person's working on the C file for the ADT, and another person's working on the main, that person on the main could go and edit those other files. But there's usually an agreement that, like, let's not do that because it could cause problems. But on the other hand, you could say, do you know all the code that is in printf? For example, you're just including it and not necessarily reading that code and using it. In fact, you don't even have the files behind it. The compiler has those files and it's using it. So you don't even know what that code is. So sometimes when you're compiling, you don't actually have the other parts. And as Tom's saying there, we've given you some compilation stuff that says you can compile against our broken version of the assignment. You can't actually see the C file, but you can see the H file that attaches them together, and that's all that you get. So it's not always going to be the case. Like, we've given you some simple stuff so far where, yes, you do have all the files together, but that's not always the case. Alright, I need to keep going. I'm running out of time now. So we've got our header code here. So I might have a header that says you can create a ship, you can free a ship, or you can send the ship on a voyage. I'm not saying that you have access to the ship internals in any way, you just have these capabilities. And I could have some ship internals that has, alright, there is a struct, there's a way to create it and free it. And so these things here, I ran out of space on this slide, but you can kind of see what we're capable of doing here with the C file inside. And so what I can do with the main file while using this, so long as I've included ship.h, I have access to those functions. So I can say capital S ship, because there was a type define here that I saw that says that I can use this capital S ship, and then the internal bits of it are going to say this is a pointer to a ship internal struct. But I don't know what that struct is, so I might as well not use that. I'll use the capital S instead. And I can create a ship called the Enterprise. So we're crossing franchises here, and I can say this ship, Enterprise, goes on a voyage that lasts 5 years. Yeah. Oh, you're welcome, Miguel. Have to head off now. That's alright, we're going to wrap up very, very soon. Okay. So what we do is we don't know exactly what's happening inside these functions, but we trust that someone else is putting together these functions so that we can use them. The other thing that we learnt right at the end was recursion. So this is actually the first time I've repeated recursion, because we're not even talking about recursion that much in this week's lab. So this way kind of inverts how we're thinking about program flow, where we're saying that the order that things run is based on stacking functions of identical function calls nearly on top of each other, and then when we return, things pop off the stack. So there's the order that things are added to the stack, and then the order of the things that come off the stack, and that's how we use recursion to iterate through things. So we can build up things until they reach an endpoint. Sorry, should be visible. Build up things until they reach an endpoint, and then when they hit that stopping case, we come back. So every time a recursive function runs, it either stops or it keeps going. So we've got this recursive function that we use to print out a list in reverse, and we said we stop if the list is empty or we've reached the end of the list. So if our pointer is null, we stop and we return. Otherwise, if there are elements, we will call the function again, and then when it finishes, we're going to say we print out the name that we have here. So we say, okay, we print out the name we have here only after we've printed out everything else in the list. So that way we're going to get a reverse. And we had this order of execution that was going to show how this works. So if we're stopping, we stop. Otherwise, we call the function again. And so we get this other call, and then we weren't stopping there, so we called the function again, and so on. And then the printing comes back in the reverse order. So the first function that was called doesn't print until all of the other functions inside have returned. If you want to go back through, you can look at the program call stack that I showed as well. So this is where we're at. Let me move my face. I'm gonna put myself over fry here. So here we are. Not sure if I'm good at spelling by the looks of the thing. Not sure if I'm good at programming or good at Googling. And he's like, And we got another one here just about coding in general. Coding in C is like, yeah, okay. Coding in Python, coding in Scratch, or coding with command blocks in Minecraft. We've had this joke before in this course. We're talking about it. So you've learnt a lot now, and you're at a certain point now where you know a lot about what you're doing with programming. I mean, you also probably know that there's a lot more to learn, but that's all right. We'll get there eventually. So I hope that what we've gotten to this point with your programming on COMP1511 is at least you've seen enough of programming to decide whether you're interested in learning more. There's a lot more to learn. So, my face out of the way. Programming is one of those fields that's growing at a rate that there is more in computer science than any one person can ever possibly know. So there are more papers being published in computer science day by day than we can even possibly read. There's always something new to find out. There's something new to work on. There's something new to learn about. So you can decide how much you want to commit. If you want to decide you're going to commit your entire life to the study of compilers and programming languages, how do we actually translate languages into instructions for a computer in the most efficient way possible, in a way that takes the full nuance of what the programmer was thinking and actually makes that happen in the computer? That's a field of study you can do entirely. You can devote your entire life's work of research into night moves, into looking at articulating possible futures of game situations and how they play out. I spent like 3 or 4 years of my life just on that, which is why Night Moves is a little bit special to me, right? So what I want to say is, you choose where you want to go from here. You can put as much in as you want. The trick is, do the things that you care about, and care about what you create, because I think that's super important. If you don't care about what you create, you should think about maybe figuring out how much you care about yourself and what you want to do in the future, and that might change how much you care about what you're making now. So I want everyone to enjoy yourselves, work as hard as, well, I say work as hard as you can, work as hard as you want to or need to, in a sense. You choose your own goals, and you work as hard as you want to for that. And if you ever see me around campus in the future, I apologize because I'm not going to recognize any of you or know who any of you are, so come and say hi. I always love to hear what my students have done in the future. It's really nice to see students I've taught in the past win awards and stuff, and or go off and do amazing things in their work and things like that. So I will wrap it up there and say that's the end for COMP1511, well, for the lectures at least. Some people still have some tutes and labs to go. You still obviously got an assignment and an exam to say, but this is the last thing from me in an official lecture context. So good luck, have fun. I hope everyone's gotten something out of this course at least, and yeah, I hope it was interesting for you. You're welcome. A lot of people are saying thank you in chat. It's very, very nice of you. That's really lovely. Thank you all. And thank you for thanking the team as well. Oh, Chicken is actually here. Hang on. She's just curled up there, asleep, sitting with Yoda. So I've taken this chair, and it's like no longer a chair for humans. It's a chair for Yoda and the cat. All right, thanks all. There's a CSC SOC study session, which is firing up now, I think. They're probably waiting for us to finish before they start up. I won't be there immediately. I need to actually eat some food, but I will come and join you later there for anyone that's going to be there. And I will see you soon, and hopefully I will see some of you on campus eventually and things like that. All right. Goodbye, all. Wait, where's my stop button? Okay, see you later.